My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. So, hope you are well and safe from Corona pandemic. So, as we know that we are staying in a Corona pandemic situation, so it's very difficult for us to continue our normal academic program inside the campus. We have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started its online program, including online international physics webinar. And we have successfully completed our 197th international physics webinar. Today it's our 198th international physics webinar. Today it's a very important day for our department. Today we'd like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, University of Waterloo, Canada. And we have with us here today Dr. Qing-Bin Lu, sir, University Research Chair, Professor, Department of Physics and Astronomy, cross-appointed with the Department of Chemistry and Biology, University of Waterloo, Canada. So I'd like to welcome our speaker, sir. Good morning, and good morning to here. So thanks for accepting our invitation, sir. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. Before going to you, I would like to introduce you with our student and viewers. So dear student and viewers, I think you have already come to know the title of this today's International Physics webinar. Title is The Cosmic Ray Driven Mechanism of the Ozone Hole. This is very exciting topic, and I think you will enjoy it. And our speaker is Dr. Qing-Bin Lu, University Research Chair, Professor, Department of Physics and Astronomy, cross-appointed with Department of Chemistry and Biology, University of Waterloo, Canada. So Professor Lu's research program cross-discipline in physics, chemistry, environment, climate, biology, and medicine, particularly focusing on femtomedicine and cancer therapy, as well as the sciences of atmospheric ozone depletion, the ozone hole, and the global climate changes, global warming. We can see his educational history. He has completed his bachelor degree in physics from Fuzhou University, China, and master's the Chinese Academy of Sciences, and PhD, University of Newcastle, Australia. So at employment, he joined as a postdoctoral research associate in 1997, and also a research associate in 1990 in the laboratory of the surface modification at Rutgers University, USA, and then as a senior research fellow at the Canadian Institute of Health Research in University of Sherbrooke. And then in 2002, he joined as a CIHR, Senior Research Fellow, phase at the California Institute of Technology, and also as an assistant professor, Department of Physics, appointed to Chemistry Department, University of Waterloo in 2004, and he stayed as 2007 up to 2007. So now he's currently working as a professor at the Department of Physics and Astronomy, and appointed to the Department of Biology, Chemistry at the University of Waterloo, and also University Research Chair since 2014. And awards and distinction: 2014 to present, University Research Chair, University of Waterloo; 2008 to 2013, New Investigator Awards, Canadian Institute of Health and Research; 2007 to 2012, Early Researcher Awards; and in 2001 to 2006, Senior Research Fellowship, Canadian Institute of Health and Research. And this is expertise. His expertise are biophysics and biochemistry, molecular mechanism of DNA damages and cell death, femtochemistry, femtobiology, and femtomedicine, cancer therapy, chemotherapy, radiotherapy, and photodynamic therapy, targeted therapy, environmental or atmospheric science, theory of ozone depletion, the climate research, theory of the global climate change, global warming, ultra-fast laser spectroscopic techniques, nanoscale and atomic scale surface science. And this is research interest. We can see this is research interest. So at the advanced femtosecond time resolved for laser spectroscopy made it possible to observe molecular reaction directly, femtochemistry, for which Professor Ahmed Jewel at Caltech won the Nobel Prize in Chemistry in 1919. Since 2004, Lu has applied this cutting-edge technique to study important biological processes in relation to disease and their treatment, particularly in the field of oncology. This innovative approach has led to the creation of the brand new research field, where the femtosecond time resolved laser spectroscopy was successfully incorporated with molecular biology and cell biology methods to advance our understanding of human disease and their treatments. Luke coined the terms femtomedicine, FMW, on his breakthrough in 2010, this paper. Through his research in FMD, Lu has discovered a novel molecular mechanism of DNA damage and a new family of the non-platinum-based halogenated molecules called FMT compounds. The latter have a unique molecular mechanism of action, generating a destroying effect in the intercellular environment of cancerous cells while having a protective effect on healthy or normal cells. FMD compounds therefore naturally and selectively target and kill cancer cells. They are effective in treating a variety of in vitro cancer cell lines and the vivo animal cancer models while exhibiting no systemic and radiation toxicities towards normal cell tissues. These findings were recently published in the Cell Press and the Lancet's eBiomedicine and in AACR's Molecular Cancer Therapeutics. Lu is now translating findings arising from fundamental FMG studies into cancer therapies in the clinic. The success will lead to novel targeted chemotherapies and radiotherapies with a minimal side effect and better targeting to treat a variety of cancers. So Lu also made the important discoveries for the sciences underlining ozone depletion and global climate change. His theories have fundamentally challenged the previous conclusions by the Nobel Prize winner in the formation of the ozone hole and the global warming 1995 Nobel Chemistry and 2007 Nobel Peace Awards, and provided the best prediction that agree with up-to-date observation. His pioneering contributions were summarized in his monographic book entitled New Theories and Prediction of the Ozone Hole and Climate Change, published recently by World Scientific. And this is the link. And this is the his publication list. This is the shortlisted publication. So thanks for all of your patience. Now it's time to go to our speaker. So, sir, thanks again for accepting our invitation, sir. It's your time, sir. You can start your session, sir.
Thank you for the invitation. It's my pleasure to give this this lecture. So I hope
it's
you.
It's my pleasure, sir. An honor.
Thank you. So can you see the screen?
Yes, sir. We can see.
Can you see? Okay.
Yes, sir. We can.
Okay. So hello, everyone. So yeah, today I'm going to discuss with you to share with you my research on the new mechanism. Actually, not new because we proposed this about 2 decades. Okay. So that is the cosmic ray driving mechanism for the formation of the ozone hole. As you know that the ozone hole, okay, is an issue of global concern. Okay, some of you probably noticed the news appear in the last year. Actually, both the springtime ozone hole over South Pole and North Pole in 2020 set a record as one of the deepest and largest and also the longest lasting ozone hole since the discovery of the ozone hole in 1980s. The ozone hole appear at the South Pole typically is very large. So the typical size is about 25 million square kilometers. So that approximately that is equal to the total area of North America. So as you can see that this hole is huge, okay? So in 2002, both the South Pole and North Pole ozone holes set the largest record. In this slide, I tried to illustrate that why the ozone layer is so important, okay? So first, I want to let you know where's the ozone layer. So ozone layer is appear in the so-called stratosphere, okay? The stratosphere is between the poles, okay? So that is about 10 km from the ground. And the stratopoles, okay, that is 50 km from the ground. Typically, we call that at the altitude below 25 km, we call it lower stratosphere. And about 25 km to 50, we call that up stratosphere, okay? Basically, the ozone layer is mainly located below 25 km, okay? So between 10 to 25 km. As you can see here, the ozone layer, okay, actually is the UV field. So you can consider UV field that will screen out the UV photons from the sunlight, okay. So with the depletion of the ozone layer, that means that the concentration of the ozone in the stratosphere will be decreased. Then we will have the overexposure to the UV photon from the sunlight for the living creature. And that can create the serious health problem. For example, that can create the skin cancer, or the cataracts, the eye disease, or that can suppress the immune system. Okay, so this ozone layer is very important, protect layer to the living creature on the Earth. Okay, so when the ozone hole, okay, will create a significant increase the UV exposure, and that can cause the serious health problem. Okay. When we try to understand how the ozone hole is created, okay, we have to consider two important facts. One is space, the other one is time. So for space, we want to understand why the ozone hole appear over South Pole and North Pole. Okay, and if you look at more detail, why the ozone hole is located at the lower stratosphere. Actually, the peak is about the ozone hole is exactly located in the 15 to 20 kilometers from the ground. Okay, so that is space. We have to also consider the time. Actually, the ozone hole will not appear in the stratosphere the whole year. Actually, just happen in the later winter to the earlier spring. Okay, usually the largest hole appear in the later winter or the earlier spring. Okay, so when we want to understand that, okay, we have to consider these two important factors: space and time. From your intuition, you might consider that when you consider why ozone hole appear over South Pole, North Pole, you might consider that possible relationship with the magnetic field of the Earth, because we know that we can consider this Earth have the magnetic field. Okay, so you might speculate that they might have a certain relationship between the ozone hole and the magnetic field of the Earth. Okay, as later we will discuss this issue again. But unfortunately, in the standard theories, magnetic field have not yet taken into account. Okay, the reason is that there's a so-called photochemical mechanism had been proposed before the ozone hole was discovered in 1980s. So I will start from the standard theories about this ozone hole. Let's look at the gas phase reaction first. In the 1970s, actually it's 1974, scientists have proposed this so-called photolysis mechanism. Okay, so when the CFC molecule, that's a free molecule, once widely used in our refrigerator as a coolant, okay, or in a car conditioner, air conditioner, okay, so that once very widely used in the industry. So when CFC emitted into the atmosphere, when that enter the up stratosphere, they will encounter UV photons from the sunlight, and that will cause the photodissociation to form the chlorine ethane. And chlorine ethane is very reactive. So when chlorine ethane reacted with ozone molecule, can destroy ozone molecule, become oxygen molecule, and to form the CLO species. The CLO species is also highly reactive. Actually, with the present UV photon, the CLO species will react with another ozone molecule to destroy another ozone molecule into oxygen molecule and return to the chlorine atom. So as you can see, this is a reaction cycle. And this reaction cycle can happen by many times, okay, up to thousands of cycles. The reaction cycle will be terminated when the chlorine atom reacted with the methane molecule to form the HCl, or when the CLO species reaction with NO2 molecule to form the CLO-NO2 species. The HCl and CLO-NO2 species is photoinactive, inert species. Okay? So this would not reaction with ozone. We call this reservoir molecule. Okay, and so because we just mentioned that this reaction cycle can happen by thousands of times. Okay, so it has been estimated that one chlorine atom can destroy up to 100,000 ozone molecule. Okay, so even the small concentration of CFC in the atmosphere at a certain condition, we can cause serious significant depletion of ozone layer, as we will see later. Okay, so this is the so-called photolysis mechanism of CFC, and this has been proposed in 1970s. If you look at the chlorine atom production rate, okay, look at the altitude from the ground, and you will see that the chlorine production rate from the photolysis CFC will have the peak at about 35 to 40 km from the ground. And also you expect that the photodissociation will be most significant near equator in the tropical stratosphere. Okay. Surprised, the ozone hole was discovered in 1980s, and they found that actually ozone hole appear over South Pole, and also the ozone hole appear at about 15 km from the ground instead of 35 to 40 km. Now you can see that the peak position is 15 km from the ground. At this lower stratosphere, obviously the photodissociation rate is negligible. So obviously you cannot use the photochemical model of CFC to explain the formation of the ozone hole directly. Okay. So sooner after the discovery of ozone hole in 1980s, scientists tried to find out why the ozone hole appear over the South Pole in the lower stratosphere. Okay. So we know that in the winter, polar stratosphere is dark. There's no sunlight. So therefore, the temperature is very low. When the temperature is very low, you can have this so-called polar stratospheric cloud, PSC ice particle, were present in the lower polar stratosphere. When with the ice particle, and you can have a certain so-called heterogeneous chemical reaction. So for this reservoir molecule, ClO, or HCl molecule, they can have the reaction on the ice surface, on the PSC ice surface. And that chemical reaction can lead into formation of the chlorine molecule, Cl2 molecule. So when the sunlight returns in the earlier spring, this Cl2 molecule will dissociate into chlorine atom. And then that chlorine atom can have that reaction cycle earlier introduced that, okay? So by this, you can create a significant depletion in the ozone layer, okay? And we call that ozone hole. So as you can see that there's a few chemical process involved in this mechanism for formation of the ozone hole. Okay, so this is for the surface reaction, and this only occur when the temperature is very low. That usually can start in the winter polar stratosphere, and this will last to the earlier spring season. Okay. So if I give the summary of the photochemical model, so basically there's a 3-step. Okay, so the step 1 is earlier we mentioned that when CFC entered the upper stratosphere over the tropical region, okay, near equator, this CFC will have the photodissociation, right? And earlier I mentioned that photodissociation products were including inorganic chlorine species, that's HCl and ClNO2, so-called the reservoir molecule. So then the air transport can send this inorganic, the photo products, okay, of CFC to the lower stratosphere over the polar region. Okay, so this is the second procedure. Is involved the air transport, okay, the circulation. And then you can have the third step I just introduced in last slide. You can have heterogeneous chemical reaction, okay, to happen on the surface of the PX ice. This can occur in the winter polar stratosphere or in the earlier spring, right? So basically, you have these three steps mechanism to form that the ozone hole, okay. And so the photochemical model has been well recognized. As you can see, these three scientists has been recognized by their work on this, the formation and the destruction of the ozone layer. Okay, they received the Nobel Prize in 1995 in chemistry. Okay, by these three scientists. Dr. Kurizin, his major contribution is more like the formation of the ozone layer. He also made a contribution to understanding the formation of the ozone hole. Okay, the Professor Molina and the Lowland, okay, they are pioneer for that the photolysis mechanism of CFC. Okay, so now you want to see how has the prediction of the photochemical model has been confirmed or disproved. Okay, so based on the mechanism I just introduced the past few slides about the photochemical model, you can look the so-called equivalent effective stratospherical chlorine, okay, so-called ESC. Okay, this will respond for the ozone depletion. Near the surface in the troposphere, we can measure that the total chlorine and bromide species. We can measure this total, the effective chlorine concentration in the troposphere, right? And this is in the polar region. Okay, the upper curve, this dust is from the measurement in the troposphere near the South Pole, Antarctica. That is the lower atmosphere. And you can expect a certain time delay from the stratosphere and the troposphere, right? Based on the photochemistry, okay, you expect that the photodissociation will mainly occur in the tropical stratosphere, okay? So therefore, you consider that the air age of the CFC will have younger, okay, near the mid latitude, okay, because you need to send that photoproducts to the polar region, right? So you can consider that the air age over the polar region, okay, will be older than the air age near mid latitude, because they consider that the dissociation will mainly occur at the tropical stratosphere, right? To be more understand the significance about this, okay, the implication is that if this mechanism is true, it's important, you will expect that the ozone layer should start to decouple, okay, means the decrease of the ozone depletion, okay, should start to observe over the mid latitude first, okay, and then you should observe the decoupling of the ozone layer in the polar region. Okay, as this slide shows that, okay, the ESC value, okay, will return to the 1980s because ozone hole start to become significant since 1980s. So as this projection, you can see that based on the photochemical model, you will expect that the ozone layer over the South Pole will return to the 1980s value by about this 2076. Okay. By contrast, you can observe that you can expect that the ozone layer in the mid latitude will decouple to the 1980s value by this 2048, about 2050s. Okay, so you can see that the decouple at the mid-latitude much earlier than decoupling over the South Pole. Okay, so that is based on the photochemical model. You predict this, and we will see what this observation has tell us. Every 4 years, the international ozone research community, they will make the report on this scientific assessment of the ozone depletion every 4 years. So far, that has been based on the photochemical model. And as you can see that from those model, the report, and you will find that actually most of the prediction, okay, has not yet been confirmed. Okay, for example, in '94, they predict that the peak hydrogen species in the troposphere we expect to peak in 1994, and then they expect that the peak in the stratosphere will have the delay about 3 to 5 years. Okay, and then after that they expect so they expect the ozone layer will start to decouple after the next several years, right? But this didn't happen. Okay, so 98 they extended that uncertainty to 1 decade or the next 2 decades. Okay, and then to 2002 report, actually they even extended that uncertainty to longer. Okay, to 50 years, because there was one very big ozone hole observed in 98. So when this report was done in 2002, interested, 2002, there was a minimal ozone hole observed. It's a very tiny hole, ozone hole over South Pole was observed in 2002. And that gives them confidence to make a prediction. Therefore, after the 4 years, in 2006, they make a new prediction. In this 2006 report, they predict that averaging over the 60 south to 60 north latitudes, the total ozone is predicted to increase 1% to 2.5% between 2000 and 2020. So they expect the ozone recovery over the mid-latitude, between 2000 to 2020 will recover by 1% to 2.5%. For the ozone layer over the South Pole, they predicted will increase, the ozone concentration will increase by 5 to 10% between 2000 and 2020. Also very interesting, when this report was made in 2006, then suddenly they observed another huge hole in 2006. So then in 2010 report, you can see that they say that the observed Antarctica springtime column ozone does not yet show the statistically significant increased trend. So in the 2010 report, basically they say, we didn't see any trend. We don't know it's going to decouple or not decouple. So that's 2010 report. And then you look at this 2014. 2014, based on the observation, we has observed that by 2012, the E theater, that is the effective stratospherical chlorine, have decreased by 10 to 15% from the peak value that's about occurred in 1995. Okay, so by 2012, the chlorine concentration, the effective chlorine concentration had decreased by 10 to 15%. And in this report, 2014, they noticed that the Antarctica ozone hole continued to occur. So they didn't say it's going to become small or big. Okay, and same thing for the ozone depletion in the middle latitude. They say remain relatively unchanged since 2000. So basically, they didn't tell you it's going to increase or decrease. Okay. Then we look at the most recent report, that was 2018. Okay. In 2018 report, they mentioned that there are emerging signs for the decoupling of the ozone hole over the South Pole. So basically, they shows that they report that there's indication that the Antarctica ozone hole has decreased in size and the the depths, the whole depths since the year 2000. Okay, so that for over South Pole, now in 2018, they report this emerging signs for the recovery of the Antarctic ozone hole. For mid-latitude or near global, from 60 degrees south to 6 degrees north latitude, they report that there's no statistical significant trend has been detected, okay, in the period of 1997 to 2016. So this is the most recently WMO report they made in 2018. They are making a new report to be published next year, 2012, because every 4 years they go into the new report. We can also look at the most recent literature up between 2018 to now. Okay, actually in the literature now has reported that the ozone layer in the lower stratosphere at the mid-latitude still shows the continuous decreasing trend. Okay, means the ozone layer at the mid-latitude is still decreasing. Okay, in the lower stratosphere at the mid-latitude. Okay, for example, the 60 degrees south to 6 degrees north. Okay, in other words, there's no signs for the recovery of the ozone layer at the mid-latitude. Right, so that's from the publication recently shows that. So as I remind you again, so 2018 has reported that there's a sign for recovery the ozone hole over South Pole, right? And now in the literature, we also see that actually for the ozone layer over mid-latitude, there's no recovery, right? So in other words, the observation shows that the recovery ozone hole occur over South Pole before we observe the recovery at the mid-latitude. Obviously, this is inconsistent with the photochemical model we just explained earlier. The photochemical model predicts that the ozone recovery at the mid-latitude should proceed, okay, should occur before the recovery over the South Pole, the polar region, okay. So obviously, this is inconsistent with observation, right? You can see there's a significant discrepancy between the photochemical model and the observation. Right? If you look more carefully, look at the ozone hole, and you can see that actually there's an 11-year cyclic ozone hole. So for example, 87, we can see the larger hole, and then 91, we see small hole. 98, we see the larger hole. 2002, we see very tiny hole. 2008, we see a larger hole. 2013, we see small. And 2020, we see another larger record. And if you look at more careful, you can also see that actually 91, 2002, 2013, that is the year have the minimal ozone hole. But this have the maximum solar intensity during the 11-year solar cycle. So you can see that the minimal ozone hole actually occur in the years of the maximum solar intensity. By contrast, 87, 98, 2008, 2020, we are in the solar minimum. Okay, we have the minimal solar intensity radiation, but we observe the biggest, the largest ozone hole in those years of the solar minimum. Okay, so why is that? Okay, so obviously this is very difficult to understand from the photochemical model I just introduced in the earlier slide. Right? Based on the photochemical model, you should expect the opposite to this observation. Right? So this so-called 11-year cyclic ozone holes. Some atmospheric chemists has argued that for this the absence of the 11-year cycle ozone hole, but this data is based on the satellite data in the NASA. So you can see this obviously you have that 11-year, and I will show you more detailed observations, the data from the observation in the later slide. Okay. So now I'm going to talk about the cosmic ray series of the ozone hole. So this mechanism, okay, was developed with my former supervisor, Professor Ted Mady at the Rutgers, the State University of New Jersey in the United States, and Professor Leon Sanch in University of Sherbrooke. And I also continue to this research when I joined the faculty at University of Waterloo. So this the major publication leading to establish the cosmic ray theories of the ozone hole. I started this reaction since 1998, okay, and I still keep publishing on this topic. So let's review the possible pathway for destruction of CFC in the atmosphere. The first mechanism, earlier I also introduced the so-called photolysis by UV photon. We discussed this earlier, okay. So this was proposed in 1974, right? This photo dissociation cross-section, okay, is 10 to minus 20 square centimeter. So this leading to the formation of chlorine atom. The second mechanism is so-called dissociative electron attachment, DEA, by free electron, okay. So this CFC molecule can highly reactive with the very lower free electron energy, nearly 0 eV, and this leading to formation of chlorine negative ion. This dissociation cross-section is about the 4 orders magnitudes larger than the photo dissociation. So this 10 to minus 16 square centimeter. Even this cross-section, this reaction probability is 10,000 larger than the photo dissociation. However, the free electron density in the stratosphere is very lower. Okay, so even this reaction is highly reactive. In the 1970s, okay, scientists studied that, and they conclude that this DEA reaction in a gas phase would not be important for the depletion of ozone because the free electron density detected in the stratosphere is very low. Then is the third mechanism, this so-called dissociative electron transfer reaction. Okay, in this reaction mechanism, the electron is trapped in the ice particle or in the liquid water. Okay, and then during the lifetime, the electron is transferred to CFC molecule and leading to the dissociation of CFC. The dissociation cross-section for this DET is huge. Okay, so this can be as large as 10 to minus 14 to 10 to minus 12 square centimeter. Okay. In other words, you compare with this photo dissociation, okay, this DET cross-section, okay, is about 1 million times to 100 million times larger than the photo dissociation cross-section, okay. This, in the rest of my talk, I will focus on the DET mechanism, okay, because earlier we mentioned that in the winter, the polar stratosphere, you can have the PSC ice there, so this could be very effective in the winter or in the earlier spring, the polar stratosphere. So let's start look the evidence from the laboratory measurement. Okay, for the gas phase experiments, as we just mentioned that the low energy free electron is highly reactive with CFC, and this can lead into formation of the chlorine negative ion. As you can look the spectrum, okay, you can see that the resonance, this is kind of the DEA is kind of resonance, and this resonance is occur at the energy nearly 0 eV. The peak is nearly 0 eV. Okay, because this energy is lower, so expect that the kinetic energy of this chlorine negative ion fragment will be very small, right? Kinetic energy very small. In the gas phase, this is not a problem. You can measure that in the gas phase. You can measure the chlorine negative ions species. Okay, just use the mass spectrometer, and this has been well known, has been well measured in the 1970s. If you want to measure the DET reaction on the surface, as I show in this slide here, I mentioned that because the kinetic energy of the chlorine negative ion is very small, so the gas phase is easy to measure that. But when you consider the surface, this chlorine negative ion will mainly trap on the surface. In other words, the desorption probability is very, very small. Okay, actually it's about 10 to minus 6. So 1 out of 1 million chlorine negative ion will escape from the surface. The most of the chlorine negative ion will just trap on the surface. So for this DET reaction on the surface experiments, it was extremely challenging to detect that negative ion species. Okay. Very luckily, in the end of 1990s, I worked with Professor Mehdi at the Rutgers. And that time, there's very few facility in the world have that kind of higher sensitivity, can detect that the chlorine negative ion disturbance from the surface by that DET reaction mechanism. When you don't have the higher detection sensitivity, you have to use much larger electron exposure. So when you use larger electron exposure, because this DET reaction is highly effective, okay, you will immediately destroy that sample. Okay, so when you destroy that the CFC molecule, because the reaction is highly reactive, okay, you are no longer look at the real reaction of the DET between the trapped electron and the CFC. Okay, so that's why it's so important to have the extremely higher sensitivity detection system. Otherwise, impossible to observe that the DET the transport mechanism. Okay, so at that time, very few facilities in the world have that capability. I will not get into the detail about this system. Basically, this unique system has extremely high detection efficiency. So I was very lucky use this system. So the experiments I did with Professor Mehdi, okay, is that we use the metal substrate to cooling down to very low temperature. And then we grow ice film, okay, the water or the ammonia, which can change the different type of ice film, okay. And then we shoot the electron beam, in this case, 250 eV electron, to bombard the substrate, okay. This metal substrate, so with electron bombardment, you can create a large number of secondary electrons. And the secondary electron have the electron energy distribution, from the 10th eV go down to near the 0 eV. Right? Earlier I mentioned that the low energy electron, can trap in the polar molecule like water, ammonia. Okay, so this becomes trapped electron. And during lifetime, electron will transfer to CFC and to form this chlorine negative ion species. I just mentioned that 1 out of millions chlorine negative ion were able to escape from the surface. Most of the chlorine negative ion just stay on the surface. With the last slide shows the extremely higher detection efficiency. So I was able to detect the chlorine negative ion years. Okay, so here's the results. Okay, and you can see that the chlorine negative ion years can be enhanced by up to about 100 times by the presence of the water, right? When we increase the water boundary layer, and you can see that the chlorine negative ion can enhance by about 100 times by the presence of the ice, the water ice. If I change this to ammonia ice, that enhancement can even larger. So this can enhance by up to 30,000 times. Is huge, enhanced by 4 orders magnitude for ammonia. Okay, and this we can also check that why this relate to the electron transfer. Okay, for example, if we change this to non-polar molecular film, for example, change it to CH4 methane, okay, or rare gas film, and you will not see this enhancement. Okay, so this confirm this electron transfer mechanism. We can change a different ice film. For non-polar, because there are no electron trapping, the lifetime in the non-polar, the electron will quickly tunnel it back to the substrate. So you will not have this transfer mechanism. So this only occurs when you have the polar molecular film. You can see this enhancement. Okay, so we propose the DET, the dissociative electron transfer mechanism. So in these experiments, okay, we detect the chlorine negative ion species, but we use this electron beam 250, and we know that you can create the secondary electron have wider energy spread down to near the 0 eV. And there's 2 shortcomings for these experiments. One is this experiment was done with the metal substrate, so people can consider that maybe this metal substrate can affect the DET reaction efficiency. Another one is because we use 250 EV, and we just assuming that the low energy secondary electron will make an important role for this. So since 2000, I moved to Sherbrooke University to join Professor Liang San's group, because his group have very good facility to use the electron beam, the energy dissolves, and can go down to 0 eV. Okay. So in this new experiments, I did with the Professor Liang San in the University of Sherbrooke. Now we want to improve. One is that we want to isolate the water layer from the metal substrate. Okay, so we use the rare gas film to isolate, to use the spacer, okay, to isolate the water film from the metal substrate. And we also directly use the electron, near 0 eV electron. Okay, we can have energy resolution. Okay, and we look at the charge trapping on top of the ice film. So here, earlier I mentioned that the chlorine negative ion species have very low kinetic energy, and majority of the chlorine negative ion were trapped on the ice surface. Right. So when this reaction occurs, the surface becomes charged, and when you measure the electrostatic potential shifting, we were able to measure the absolute dissociated electron transfer cross section for this hydrogen molecule, including organic or inorganic species observed on ice. Okay. In this measurement, we only measure the charge trapping efficiency on the ice surface, right? So essentially, actually, we cannot distinguish that it's come from this zero negative ion fragment or not, right? However, we already know that from the gas phase reaction, once electron captured by the CFC, the dissociation probability is huge. It's nearly 100%. Okay, so basically, for measure this chlorine the charge trapped on the surface, you can know the absolute dissociation cross section, this DET reaction. Okay, and I will also show you evidence to validate this when you compare this measurement with the last measurement from the ESD measurement I did in the Rogers. Okay, look at the chlorine negative ion. When you compare these two measurements, and you will confirm actually this absorption is true. Okay, the dissociation probability is almost 100% for CFC molecule because they're highly reactive. Okay, so here I show you the results. As I mentioned that we can scan the electron energy, this energy dissolved. So you can see that when you put this CFC on the rare gas film without ice, okay, and you can measure this cross section, okay, is 1.4 times minus 15 square centimeter. With the presence of ice film, okay, you can see that this increased now to 1.3 times minus 14 square centimeter. You change this ammonia, okay, this keep increase to about 1 times 10 to minus 13 square centimeter, right? In last slide, I mentioned that in this electron trapping measurement, we are assuming that the dissociation probability of CFC once captured electron is about 1 unit, 100%. So now, when we compare this value with the experiments I measured the chlorine negative ion direct at the New Jersey, the Rogers, the value is they are close each other. It's near the same. Okay, so that proves this absorption is true. Okay, the dissociation probability for the CFC is very, very high. It's close to unit. Actually, that had been known even from the gas phase experiments. Okay, they know the dissociation cross section is very large for the CFC. Okay, so this can tell that absorption is validated. We also did similar experiments for the inorganic chlorine species, for example, HCl. Okay, and again we can see the resonance near the 0 eV. Okay, so based on the ESD experiments, measure the chlorine negative ion or that electron trapping experiments. Okay, we propose these kinds of mechanism. Okay, so in the gas phase, you can have the DEA with the near 0 eV free electron. In the surface, okay, you can have dissociative electron transport DET mechanism. Okay, so basically they come from electron trapped in the ice film and then to the molecule and make the molecule dissociation. Okay, and we determine that the dissociation cross section, okay, is 10 to the minus 14 to 10 minus 12. Okay, as I just mentioned that this is 1 million times to 100 million times the photo dissociation cross section. So it's huge. Right? In both facilities, it's very unique, the Ruggers and the Shawbrook. Okay, so as you can see that we published this data since this results since the later 1990s, okay, to earlier 2000s. Okay, however, very few group in the world was able to reproduce this data. So that time, people was very skeptical about this experimental observation. Then, about 1 decade later, there's a fewer group in Korea or in Germany. Okay, they use different methods. They actually use the time result femtosecond laser spectroscopy, the pump probe, femtosecond laser spectroscopy. Okay, and they took the similar electron transfer mechanism. So in those the so-called two-photon photoelectron spectrum, actually they monitor this reaction, the lifetime and the year change. Okay. For example, the Professor Martin's Wolf group at Germany, okay, they shows that nicely results for this how electron trapping in this the D2O ice film on the metal substrate, and you can see that actually that lifetime electron can trap very very long from femtosecond time scale to the the minutes. Okay, so this spread very wide time scale. Okay, very long lifetime, and they also put the CFC 11 on top of ice film, and you can see that this trapped electron quickly transfer to this CF03. Professor Wolf's group, they also determined the dissociation cross-section for this CF03 on top of this D2O, and they determined the value is 4 times 10 to minus 12 square centimeter. This is very large cross-section. This is larger than the H2O I measured at the drugs or in Shawbrook. But this is comparable to this ammonia, CF2CO2 co-absorber with ammonia. That one we observe 6 times 10 to minus 12. So this is huge. Okay, it's 100 million times than that photo dissociation cross-section. So after this, okay, people know that this mechanism is very well established. So if I give the summary about this observation, the laboratory measurement of this DET mechanism for the CFC on ice, or including the organic HCl on ice or the liquid water. Okay. On the surface experiments, basically my colleague and I used the 2 different methods. One is detect the chlorinated ion fragment directly. The other one is detect the trapping cross section. Right. We confirm the electron transfer mechanism. And then there's 2 groups in Germany and Korea. They use the femtosecond laser spectroscopy. They monitor the lifetime and the year of the trapping electron, have the real-time observation, and they also determine this very large cross-section. When I set up my group in the University of Waterloo, I also look at this DET direction in the liquid water. Okay, and in this liquid water, again, we also use the pump probe, the femtosecond laser spectroscopy. We didn't use the photoelectron spectroscopy, but we used the transient absorption and the fluorescence. In these experiments in the liquid water, we detect the transition state of a reaction directly. So we look at this, the transition state for this electron transfer mechanism. Right. Like the CF2, or the CCl4, we can look at this, the transition state, and usually from this transition state, earlier I just mentioned that the dissociation probability is almost 1. Right. So this is also very direct evidence. Okay. So as you can see that this DET mechanism has been well established from the laboratory measurement. But we need another piece of information, okay, to solve a puzzle about this, the implication for ozone depletion for this DET mechanism to the ozone depletion in the atmosphere. The chemist has argued that the CFC will not stick on ice. So this experiment shows that there is only true when for the pure ice, okay, indeed CFC have very little sticking probability. It's not sticking, okay, on ice surface when it's not charged, pure ice. However, when the ice particle become charged, like the PSC ice particle in the stratosphere, okay, that's charged, right? Because your cosmic ray we explain later on. So when the ice film gets charged, you can see that the CFC can immediately have very strong absorption on the ice film. So here you can see you can cross the larger work function changer. Okay, so this demonstrates that the charge on the surface can induce the significant absorption of CFC on ice. Okay, so this so the last issue, okay, about the possible implication for the DET mechanism to the ozone depletion, because indeed it shows that charge can induce significant absorption of the CFC on ice. Okay, so now I'm going to show you evidence from the atmospheric observation. If you look at the stratosphere, okay, the very simple, the major electron source, okay, is cosmic ray. So basically, electron in the stratosphere is created by ionization by cosmic ray. Okay, cosmic ray originates from deeper space. Okay, is composed of mainly charged particle, mainly proton, or it's the other particle, or the heavy ions. Okay, so when high energy cosmic ray enter the atmosphere, there's a lot of collision with the atmospheric molecule, and they can cause the huge number of the secondary particle. That could be electron, ions, neutron, and so on. Right. And because this cosmic ray are charged particle, okay, and earlier I mentioned that we have the magnetic field of the Earth, right? At the beginning, I asked you that based on the intuitions, okay, would you consider the relationship between the ozone hole and the magnetic field of the Earth? So now, if we consider cosmic ray, we consider the electron dissociation, the DET mechanism, the electron produced by cosmic ray, and cosmic ray is charged particle. So the magnetic field of the Earth will focus the cosmic ray over South Pole, North Pole. So that's why when you measure the cosmic ray, you can see the strong intensity over South Pole, North Pole. And when you measure the electron, the ionization rate, the electron production rate, again, you can see you have higher distribution over the South Pole, North Pole. Later, I will show you. And you can also look where's the peak at the altitude, the height from the ground. Okay, so before I show you the evidence from the atmospheric observation, let me give you the clear picture about how this DET mechanism, okay, have the implication applied to the ozone depletion. Okay, so earlier I mentioned that in the winter polar stratosphere, okay, you have the PSC ice, right? With the cosmic ray, you will produce electron. Electron can trap in the ice, so the ice become charged. With the CFC or the hydrogen molecule, they can stick on the ice surface, and then electron can transfer there and lead into formation of the chlorine active ion. This DET mechanism can also form the chlorine ethane and also the neutral hydrogen radical. Those radicals can directly reaction with ozone molecule to deplete the ozone layer. So this process can occur in the winter when there's no sunlight. They can have some ozone depletion occur with this DET mechanism. The chlorine active ion can also reaction with certain well-known reaction, surface reaction, leading to formation of the chlorine molecule, CO2. So when the sunlight comes back in the earlier spring, this CO2 will dissociation into chlorine ethane, and then chlorine ethane can have the reaction cycle to cause the significant depletion of that ozone layer, right? So this will occur with the sunlight, okay? So in the DET, they can make ozone depletion in the winter, and with the sunlight come back, that the depletion reaction can be significant enhanced, okay? And we already mentioned this, the magnetic field, okay, make this over South Pole, North Pole, okay? So now here is the observation, okay? As I just mentioned that the cosmic ray have strong latitude dependence. Okay, so there's focus, the intensity is have the maximum over South Pole, North Pole. Okay, near great and minimum. If you look at ozone depletion over the past decade, okay, and you can see that many ozone depletion occur over South Pole, North Pole, and there's major difference over between the South Pole and North Pole. That is because the continental difference. Because over South Pole, we have the continent, so there's the stable vortex, the polar vortex over South Pole. In other words, the temperature in the stratosphere over South Pole is much lower than the temperature over the North Pole. So there's much more PSC ice over the South Pole in the winter, polar stratosphere, okay, compared with the North Pole, okay, and also the polar vortex much more isolated, stable, okay, and that's, you can see that because that DET reaction also relate to the presence of ice particle, okay. So the South Pole is much more significant than the North Pole. Essentially, there's very little ozone depletion has been observable in the tropical stratosphere, right? As you can see that, okay. This also corresponds to the minimum in the cosmic ray. If you look at the ionization rate, that is electron production rate by cosmic ray ionization, and you can see that this electron production rate have the peak at 15 km from the ground. Precisely, the ozone hole is located at 15 km from the ground. So this perfect match, right? So this is for the South Pole, the red curve, this ozone hole. The square, the black color, this square, this corresponds to the middle latitude, okay? So even for the middle latitude, you have the two peaks. One is in this, 15 km from ground. Another is 40 km from ground. What is 40 km from the ground? This amplified by 10 times. Actually, the depletion by only a few percentage. This in the up stratosphere, this can be explained well by the photochemical model. Okay, right? For this up stratosphere, this can be explained by the photochemical model. But we are focused on this ozone hole, and ozone hole is mainly occur below 25 km in the lower polar stratosphere, right? Earlier I mentioned that the CFC below 25 km, the photo dissociation is very ineffective, right? The dissociation rate, photo dissociation rate is very small, okay? When we check this, the beginning of winter and the end of winter, and you can see that you have the significant depletion of the CFC. This cannot be explained by photo dissociation because they're dark, there's no sunlight, okay? This can well explained by the DET, okay? There are also some trace gas, the CH4N2O CFC, okay? And very interesting, for methane, CH4, I mentioned that there is non-polar molecule, and also the DET, the DEA for methane will not occur, okay? Because they don't have, the methane molecule doesn't have the resonance near the zero EV. So as you can see that in the winter, the methane concentration is very stable, right? There's no depletion. By contrast, for CFC and N2O, you can see that the concentration start to decrease since the beginning of winter. So once you have the PSC ice there, you will see that the N2O and CF2 and the CFC, they start to decline, okay, from beginning of winter. You look at the ozone concentration over South Pole. Usually, ozone hole is defined by the total ozone concentration below 222 DU, okay? Based on that definition, so you can see that the ozone hole start appear in August, right? Because ozone hole define that the ozone concentration below 222 DU. However, if you look at the ozone concentration, you can see that the ozone concentration drop, that occur much earlier. So even in the June, in July, you have a significant decrease. So the beginning, you decrease from 280 to 222. That occur from June to July. That is in the winter. earlier I mentioned that that's dark, there's no sunlight, right? But this, you can see the ozone depletion. Earlier we explained that the cosmic ray driving mechanism, the DET, okay, we call the CRE mechanism, can explain that ozone depletion in the winter season, right? When there's no sunlight. And with sunlight, this depletion will enhance, right? So typically you will have this, the most significant depletion in the September to October, right? And this lasts to end of December, okay? So this, you can see the space and time correlation, okay? So here I shows that one evidence, right? It's very strong space and time correlation between the cosmic ray driving mechanism and the ozone depletion, and also the CFC depletion in the atmosphere. Okay, now we want to look at more time correlation, look at the time series data. So this data is from NASA, and this for the whole Antarctica area, okay? So this corresponds to 60 to 90 degrees south and the latitude. This covers the whole polar cap, the South Pole. As you can see that this the October monthly average data, okay? The dashed line is cosmic ray. So here you can see that when you have the cosmic peak, you have the deepest ozone hole, right? Means you have minimal ozone, right? They have the largest depletion, right? When the peak cosmic ray, okay? And over the past 3-4 cycles, you can see this very good correlation. So you can also do statistical analysis. You plot this ozone concentration as function as this here, this C concentration C that's associated with the halogen species in the stratosphere. Okay, the I is cosmic ray intensity. This I square 10 arises from two effects. One is that DET reaction will depend on electron density, of course, right? And also we earlier mentioned that the absorption of the CFC present on ice surface also depend on the charge-induced absorption, right? So when you consider the two factors, one is for that DET reaction depend on the electron density. The other one is the amount of CFC stick on the surface depend on the charge density on the surface. That also linear depend on the cosmic ray intensity. Therefore, you will have this square dependence. So in this, the simple equation, okay, you have this constant K here. So if you do analysis, you plot this ozone concentration as function of the Ci square, and you can get very good linear dependence. This correlation efficiency is up to 0.83. This is for October monthly, okay? Even the data have the bigger fluctuation, right? And if you look at the 3 months average from October to December on the right side, okay, even you can get higher linear correlation coefficient. This up to 0.91, right, for these 3 months. And again, you can see very clear when the cosmic ray peak, you have the largest, the deepest ozone hole, right? You can see that, okay? So this is from NASA data over the South Pole. From the ground-based measurement, okay, from the Bloom measurement, you can also look at the similar relationship between the cosmic ray driving mechanism and ozone depletion. Again, you can get a very good linear dependence with this, the CRE equation with this, the concentration times square, the Ci square, okay? Again, you can get up to 90% correlation, right? And you have this beautiful, you can see this, the cosmic ray change, okay? You have this oscillation up and down. So that is from the Bloom-based measurement. Now we also want to look at more careful about the indication for the recovery of the ozone layer over South Pole and at the middle latitude, okay? This from the measurement, okay? So this from the NASA satellite data, okay? This is October monthly average over South Pole, okay? 60 to 90 degree data, okay? This is the middle latitude. The lower part is because in the last 2 slides, we shows that we can get the good statistical analysis results, okay? We have a good correlation between ozone loss and that Ci square, right? That the Ci equation, okay? So now we can remove that cosmic ray effect because over the past 4 solar cycle, the cosmic ray have the increasing trend, right? So even now we know that we have the Montreal protocol, we control the using of the CFC actually inhibit the use of CFC internationally. So the CFC concentration is dropping in the atmosphere, but cosmic rays increase. So if we want to see the real trend of the ozone decoupling because of the Montreal Protocol control phase out the CFC, we have to remove the nature effect, the cosmic ray effect. So based on the excellent statistical results, last two slides we have, so we can remove that cosmic ray effect. And now you can see that, okay, after you remove cosmic ray effect, you can see this ozone concentration change actually have the minimum about 1995. So this corresponds to the peak of the CFC, the effective chlorine species, okay? The effective chlorine species have the peak about 1995. So you can see that actually the ozone hole over South Pole have very quickly response to the decline of the CFC in the atmosphere because of the Montreal Protocol that immediately responds, right? How about look at the ozone layer over the mid-latitude? We do similar analysis. Actually, we don't see any directly signs for the decoupling of the ozone layer over mid-latitude, right? Okay. So actually, I reported these results about 1 decade ago, okay? And as you can see, I will show you later. Earlier I mentioned that in 2018, WMO report have confirmed this decoupling of the South Pole, right? Most recent literature, in next slide I also show, also confirm there's no sign for decoupling of the ozone layer in the lower stratosphere at the mid-latitude. Right? So again, but I reported this observation about 10 years before the recent literature. In last slide, I used the cosmic ray equation to remove that the nature cosmic ray effect from the observed data. But we can also validate this processing, okay, the results we get in last slide. If you look at the summertime, the polar stratosphere, okay, because in the summertime you don't have PFC ice, so that DET reaction will not significant in the summertime, right? So if we look at the ozone concentration over summertime, and you can see that over South Pole, without any processing, this from the directly observation data, you can see there's significant decoupling, okay, since 1995, okay? So that's from the satellite data. The right side is from the Bloom measurement, the ground station measurement at Haiti. And again, you see very, very clear, the summertime ozone start to decouple, 1995. So this where established that there is significant indication, significant sign for decoupling of the ozone layer over South Pole in the polar region, right? Okay. So this is the graph shows in my book, okay? So here we use the simple, this cosmic ray driving mechanism. We have this derived this simple equation, okay? We have only single parameter, that's K constant, okay? The C is from the measurement, I is also from the measurement, okay? So we can reproduce that observed data very well, and we can also check the conformation, the prediction, okay, from this equation, from this mechanism. And you can see that based on the data, this has been, the prediction has been confirmed very well from this, the cosmic ray driving mechanism. In the later slide, I will show you we have more update up to 2020 now, even you get more convincing evidence, okay? So after my publication, you can see that recently, okay, there's people has reported the decoupling of the Antarctic ozone layer. For example, on ozone hole, for example, this is the Susan Solomon's paper in 2016 in Science. They shows the emergence of the decoupling of this ozone layer, and this has taken were taken in the WMO report 2018, right? They reported this emergence indication for the decoupling of the Antarctic ozone layer, right? They shows evidence by presenting this the trend, the change of trend for this, the vertical profile of the ozone layer, okay? So you look at this over the South Pole station, the Japanese station Shiowa. Okay, and during 1980s to 2000, over this 20 year, you can see there's a negative. This trend is negative. That means the ozone is decreasing. Okay, every year they have the decreasing, right? And then you look at average from 2000 to 2015. For this 15-year average, you can see become positive. Means there's an increase, right? So this shows the trend is changing. Okay. However, because they average 20 years or 15 years, actually you don't know exactly which year is the 10 or 9 point. Okay. This would not necessarily means the 10 year is 2000, because when you average it 20 or 15 years, okay, this could happen, before 2000 or up to 2000. Okay. So when you average that, it's not precisely you can know which year is the 10 for the recovery, right? You basically you can know has recovered, but you don't know precisely from which year, right? Similarly, in this the 2020 Nature paper, okay, they use another method to look the sign for recovery of the Antarctic ozone layer. So they look the change of the summertime jet stream over the southern hemisphere, okay, because the jet stream position, it depends on the ozone concentration. Okay, when the temperature changes, they can make the jet stream position shifting. Okay, so when they look at this, the jet stream position, and you can see that there's a turning point around 2000, but this data is quite noisy. Okay, there's something there. Okay, so they conclude that indeed there's a recovery. Okay, signs around 2000. It's not precisely, but it shows that. Okay, so that is another evidence. Okay, when they look at this, the recent literature, they also look at the recovery ozone layer in the middle latitude. Okay, and you can see that in the middle latitude, actually there's no signs for recovery of the ozone layer. Right? So that is also consistent with my results report about 10 years ago, right? So there's no recovery for the ozone layer in the middle latitude. So again, actually this is significant discrepancy between the photochemical climate model. Even they consider the greenhouse gas effect, okay, but there's still significant discrepancy between the photochemical model and the observation, right? So here I give you more update observation, okay. So this is my most recent publication. You can see that the light blue curve, okay, that is from the photochemistry climate model. They average it for many models. Okay, this is the mean, the average of those photochemical climate models. They get averaged, and you can see that for our South Pole, they predict, okay, they have the recovery here. Okay, this observation. So now they're predicting the recovery to 1980s is almost the same year as in my earlier publication. I predict almost 10 years ago, okay, 1 decade ago. So now they get the same prediction as in my earlier prediction, okay, about the change. Now this is almost the same year occur for recovery of the South Pole. However, for the middle latitude, okay, you can see that this photochemistry climate model average, okay, they predict the recovery since about 2000s, right? And the observation, as I just mentioned, that shows no sign for recovery. Okay, the red curve is from the cosmic ray driving mechanism. Based on this red curve, actually the CRE model predict that if the cosmic ray keep the rising trend we observed in the past 4 solar cycle, even by the end of this century, you would not see the recovery of the ozone layer at the middle latitude will recover to 1980s level, right? So this is red curve. The photochemical climate model, they predict that this will recover even before the recovery of the South Pole. So they predict, by 2045, okay, this will recover to 1980s, okay. So we will see, okay, but up to date, we see there's significant discrepancy between prediction from the photochemical climate model and observation. Right? On the right side here, I show more data. So here is only months, left side monthly, October, monthly average data. This top one is over South Pole from NASA data, 3 months, October, December average. So obviously you can see you have the peak, right, up and down, and this correlated with the cosmic ray, the CRE mechanism very well, right? And this from NASA data. This is, again, this from the Japanese Shiowa, the South Pole station, okay? And this is the ozone data. You can see that we can see at least 3 peaks over the past 4 solar cycles, right? And each of these correspond to the CRE mechanism. Actually, that CRE equation can reproduce this data very well, right? This another South Pole from the United States NOAA South Pole Antarctica station. And this, again, for the 3 months average data. And again, you can see you have the 11-year cycle, 11-year cyclic variation of the ozone depletion, right? You can see the peak. This also reproduced by the CRE equation excellently. We can also look at the temperature in the ozone hole, because earlier I mentioned that the ozone is greenhouse gas, right? So when there's significant ozone depletion, we make the temperature drop in the ozone layer, okay? Because ozone molecule is the green gas phase, okay? So again, if you look at the temperature at the ozone hole, okay, about 15 km from the ground, and you can see this 11-year cyclic variation, okay, similar to ozone concentration, okay? And again, this can be rarely reproduced by the CRE equation, okay, the cosmic ray drive mechanism, right? So this, over this, the Shiowa station. The right side is the South Pole station, okay, and similar results, you can see that, right? Here's the one unexpected dip in the 2015, and this is well known because the volcanic eruption, okay, happened in the 2015. For 2020, in last slide we shows that, okay, you can see 2020. From last slide, you have this largest, deepest ozone hole, right, in 2020, okay. Similarly, for temperature, you can also see you have the largest drop, and this corresponds to the maximum cosmic ray, okay. We can also do similar statistical analysis, and you can get very higher linear correlation coefficient, okay. This data is very interesting. Here I shows you the vertical profile, okay, for the ozone depletion. Earlier I shows that the cosmic ray have the maximum electron production rate at 15 km from the ground, right? And you look at this, the ozone hole location, okay? The red curve is the October average ozone over 1968 to 1980s. That time there was not significant ozone hole, so the concentration ozone is huge, and you can see the peak here. The ozone peak is about 15 to 20 km, right? The red curve, it corresponds to 1991 to 1997. That time has this larger ozone hole. So you can see there's a larger drop of the ozone concentration at this range, okay? When you have the cosmic ray higher intensity, there's a larger ozone depletion. Even we can divide this into 2 regions. One region is from about 13.5 km to 17.5 km. This corresponds to the peak of the cosmic ray ionization rate. This is at the peak of the electron production rate at this 4 km region, okay? And this region has also half of the peak of the ozone maximum, right, in the lower part. So in this lower part, you look at most of the time when you see the largest ozone hole in this ozone layer, about this 4 km layer thickness, okay, nearly all the ozone molecule has completely destroyed, right? In the up half, about from 17.5 to 21.5 km, okay, again, this corresponds to the up half of the ozone peak. But now you can see that in this up half, the cosmic ray ionization rate has dropped, right? So in this up half, you can see that when the when you observe the maximum ozone hole, you can see that there's still change. Okay. In other words, most of the time, the ozone layer in this up half of the ozone peak only partially ozone deplete, not complete. But in the lower half, correspond to the cosmic ray peak position, you can see you can complete depletion, even overkill the ozone layer, right? So on the right side, I plot the ozone loss, okay, based on this the vertical profile. I plot this ozone loss as function as the cosmic ray ionization intensity I square, and you can get almost perfect linear correlation. This linear correlation efficient up to 0.96. 1 is perfect, so nearly perfect. Strong correlation, okay, means that this ozone loss can, described by this I square based on the CIE equation, right? This also give you very strong evidence. We can look at more detail. So now we look at layer by layer of the ozone depletion, the partial ozone concentration for each atmospheric layer. So when the pressure higher means that is in the lower atmosphere. When the pressure is higher, okay, for example, to 2 H-part, that is about 40 km from ground. Here, when it's 100 part, it's about 15 km from the ground. So at this cosmic ray peak region, okay, you can see that the red curve is from the cosmic ray driving mechanism, the CIE equation, okay, and you can see that approximately this CIE equation can nicely fit this 11-year cycle variation, but this still over give the amplitude larger than the observation. At a little bit higher, at this earlier mentioned that from 17.5 to 21.5 km, that region, okay, you can see that this CIE equation have the best match with the observer data for the ozone depletion, right? So this is the best match. This, based on the last slide, we shows that in the up half, that 4 km, the stratospheric region, okay, that ozone concentration is very sensitive to the change of the cosmic ray, right? So this is almost perfect match, okay? And when you keep increase the height from the ground, when you enter the up stratosphere, you can see this oscillation amplitude becomes small and small, and finally disappear. You don't see that. So in the 40 km the ground, you don't see this 11-year cycle variation, right? So 40 km, that's photochemical mechanism dominant region, right? Similarly, in the right side, we look at the temperature at the ozone hole, and you can see the similar phenomena, okay? And again, this temperature can really explain, described by the CIE equation, okay? We can reproduce that, can check the prediction, okay? Agree with observation, nearly perfect, especially in this, the 50 part in that region from 17.5 to 21.5 km, right? So this very nicely reproduce the data and also can check the prediction by this mechanism, right? We predict that you can have 11-year cycle variation in the ozone depletion over the ozone hole, the South Pole ozone hole, and also the temperature in the ozone hole. So both has been well confirmed. So here is the summary for this, the cosmic ray driving mechanism of the ozone hole. So before I summary, okay, actually we can also make the quantitative estimate that ozone depletion by the CIE mechanism, okay. So earlier I showed that at the peak position, okay, when the cosmic ray maximum, actually you can make almost completely deplete the ozone layer, okay, or even overkill. So quantitative, with that I can estimate that nearly all of that ozone molecule can be depleted at that peak position from 13.5 to 17.1 km from the ground. Okay, I can make a quantitative estimate that. Okay, so this conclude that the CIE mechanism can completely destroy or even overkill the ozone layer in the cosmic ray peak polar stratospherical region. Okay, during the cosmic ray maximum, and this agree with that observation based on that the altitude purified data, right? I show in the last two slides. Okay. So except that the new updated data, all of that observation has been included in my published book in 2005. the new update I'm publishing now, okay, and has been published in arXiv, the e-printer platform. So here's a conclusion about the ozone hole series. Okay, the CRE mechanism has well confirmed by the observed data of the ozone and temperature over the South Pole over the past 40 years, as evidenced by the excellent reproduction of the observed data by the CRE equation with only two variables. One is the basically CFC concentration. The other one is the cosmic ray intensity. The CRE prediction of 11-year cyclonic variation of the ozone hole and the associated temperature, the so-called stratospheric cooling, okay, has also been well confirmed. Right? A quantitative estimator indicated that the chlorine atom produced by the CRE mechanism can completely deplete or even overkill the ozone layer in the cosmic ray peak polar region correspond to the when the cosmic ray have maximum, and this is consistent with observe the altitude profile of the large ozone hole. Okay, after remove the nature cosmic ray effect, we can see very clear signs for the recovery of the ozone hole over South Pole since 1995. Right? When you check the ozone layer at the mid latitude, and you can see that delay, that the recovery will be delayed by at least 10 years, can be more than 10 years, right? So this is very good, agree with the CRE mechanism. But as I explained earlier, this just opposite what you predict from the photochemical mechanism, right? So all of these results provide convincing fingerprint evidence of the CRE mechanism. And the CRE mechanism, must be considered as the key factor in evaluation the Antarctic ozone hole. If you want to remove this, the long existing discrepancy between the photochemical climate model and the observation, okay, you have to take this into account. Otherwise, you always have that discrepancy that has existed for decades. Okay. So I give the presentation about the ozone hole series. I think I only almost used up the time. I will not have time to talk about the second part of my work about the series of the climate change. Okay, I will give very, very briefly. So basically, in my book or in my publication, another series about the global warming, in my model, I assuming that the surface temperature just controlled by hydrogen molecule. So the red curve is come from the quantum series of the global warming caused by CFC that is regulated by Montreal Protocol. This is the green curve is correspond to CFC and HCFC, the hydrogen gas regulated by Montreal Protocol. The blue curve is correspond to hydrogen gas controlled by Montreal Protocol and also by Kyoto Protocol. So that means that including CFC, HCFC, CFC, and PFC. If my theory is correct, then now we are in 2021, we are approaching the peak for the global surface temperature. So we can see that in the coming decade, we should see the global cooling trend instead of global warming trend. If the CO2 series is correct, you will see keep increasing the surface temperature. If this mechanism is correct, you will see that in the coming 2 or 3 decades, we should see the declining trend of the global surface temperature. Okay, I have to say that in this series, there's no parameter. Okay, so it's parameter free. If you check my book or my publication, okay, especially in the 2015 book, I don't use any parameter. So in this calculation, I just use the black body radiation, the quantum series, and input the concentration, major concentration of CFC, HCFC, the hydrogen molecule, and come up with this solution. Okay, I will skip this. As you can see, this CO2 series, they predict that, but you have to consider, is this real or exaggerated? Okay, so I don't time to present that. This can come from the black body radiation spectrum. Okay, so there's a very good fundamental basis why this CFC is so important. I give very briefly, okay. This is the propagation from the Earth, and at the atmospheric window, 8 to 12 micrometer, is very transparent. So essentially, all the heat energy from our Earth's surface emit into the space through this spectral region, 8 to 12 micrometer. This so-called atmospheric window. In the atmospheric window, actually quite transparent. So you see the transmittance is almost 1. Here is one peak. I mentioned that this corresponds to ozone. It's well known. Ozone is ozone molecule, so you have one peak. And then there's a spectral correspond to CFC, because in this region it's very transparent. Majority of the radiation energy emitted into space through this atmospheric window. Therefore, the CFC is extremely effective of greenhouse gas. This is very well known since 1970s. If you compare the greenhouse effect per molecule, then the greenhouse effect of CFC is about 1 million times of the greenhouse of per CO2 molecule. CO2 molecule, we know is greenhouse, such as CH4 and N2O. They are all effect greenhouse. However, they very high concentration. That's true. The absorption band is nearly saturated, and also that because the absorption band is overlapped with water, you can see that both sides overlap with water, and we know that we have very high concentration water, right? So because of water and because also the concentration of CO2, CH4, N2O, so the greenhouse effect based on the data I have observed actually has been saturated. In other words, even from the ozone data, although from the global surface temperature data, I don't see any signs of CO2. For example, here, okay, you look at this temperature and this CO2 concentration from 1850 to 1930. Before 1930, there is essentially no significant CFC in the atmosphere, right? Because CFC is human-made and widely used only after 1930s. If you plot this temperature as function of CO2, and you can see there's zero correlation before the CFC, the temperature is flat, okay, from 1850 to 1930. And then you look at the CFC concentration significant in the atmosphere, and that's why we start up the significant ozone depletion from 1970 to up to now. And you plot this global surface temperature as function as the total hydrogen gas, and you can see this correlation nearly perfect, 0.98, almost 1, okay? Earlier I already mentioned that we can use the complete quantum series. You consider CFC, HCFC, get the green curve. If you consider CFC, HCFC, HFC, PFC, you get the blue curve, okay? So if this series is correct, after 2020, in another 1 decade, 2 decades, we will start to see the decline temperature trend, okay? So we will see if this will be right or not, okay? So here, this is the summary, okay? The surface temperature is close correlated with the amount of hydrogen gas since the 1970s. Extremely high linear correlation coefficient up to 0.98, almost perfect, has been found, okay? The parameter-free quantum physics calculation shows that the hydrogen gas can cross a global surface temperature by up to 0.8 degrees since 1970s. And the global warming will be mainly caused by greenhouse of hydrogen gas rather than CO2 based on my series. So finally, I have to acknowledge my collaboration with my former supervisor, Professor Ted Mehdi. Unfortunately, he passed away in 2008, and the Professor Neon Sanchez at University of Brook, and I have to fund the funding agency. They are very important, otherwise we're not able to do this kind of work. So this is the take-home message. It is all because of the cosmic ray and CFC. So thank you for your attention. I will be happy to answer your questions.
Yeah, thank you, sir, for your wonderful and exciting presentation, sir. We have got few questions in inbox and in comment section. So if you allow, we can start our discussion session.
Okay. Can
so
I
the
see?
first question is, yeah, you can also see, but I have another question from inbox. I can add those questions in the chat box so that you can also see.
Okay, so the first one is that how neutrino telescope measure the temperature change in the ozone layer. The temperature measure, okay, actually that's quite straightforward. Actually, they use the broom, okay, because the whole location is 15 km from the ground, is in the lower stratosphere. So the measurement can be very straightforward. Not only from satellite, can also measure by the broom-based measurement. So, for example, in the Halley station that has been measured by the British academic survey, okay, Antarctica survey, the BAS, and you can see the temperature data. All in the Japanese station, the Showa, okay, all from the NOAA station, the South Pole, all of that you can get the temperature data. Number one. Number two is how electrons are participating from the Earth's magnetic field are destroying ozone in the upper atmosphere. And it's a very good question, okay? In the upper atmosphere, you have also UV photon, right? Earlier we mentioned that, for example, in the 40 km, you have UV photon. So there, okay, the UV photon density is very higher. So in the upper atmosphere, you can have photo dissociation mechanism and also electron, okay? But I will say because you have much more photon available in the for example, in the 40 or the 50 km. So there, okay, you don't have that significance. And also because the CFC concentration, they will say in the 50 km is very low because you can have strong, significant the photo dissociation process in the upper atmosphere. I have to also highlight that based on the current observation data in the upper atmosphere, in the 40 km, actually is quite agree with the photochemical model. Although that in the 40 km or 50 km, there's only very small fraction of ozone concentration there compared with the total ozone. At the 40 or the 50 km, it's take only very small fraction of the total ozone concentration in the stratosphere. So is this answer your question?
Yeah, maybe. So thank you, sir, for your wonderful presentation and discussion session, sir. So I think students have learned a lot of things about the cosmic ray driven mechanism of the ozone hole. So as we know that we are using too much fossil fuel, and due to that, a lot of CFC and the carbon dioxide emissions. So, and there's some greenhouse effect. So we have to consider that. And I think by your lecture, some awareness has been spread towards us, and I think some of our students may fall in love in this research, and hopefully will join in future. So thanks again for giving us this opportunity to arrange such an important webinar. So bye for today, and hopefully we'll arrange another webinar in near future with you, sir. So have a nice day, sir. Good night.
Thank you. I hope you will, each of you will stay safe and stay healthy. Okay. Yes. Unfortunately, with this very stressful cosmic, okay, the pandemic, yes. Hopefully each of you will stay healthy and stay
we are trying
safe. To. Thank you.
Yeah, we're trying.
Thank you.
Yeah, bye.
Thank you.